Derivation and the integration by parts formula. Okay, so let's begin with an introduction to integration by parts. Now, you've already spent time learning about derivatives in differential calculus, and specifically, you've encountered the product rule. Remember that the product rule helps us find the derivative, that is, how a function changes, when that function is created by multiplying two other functions together. Think of integration by parts as doing things in reverse. It's like unwinding the product rule. While the product rule finds the derivative of a product, integration by parts finds the integral of a product. Now, why do we need a special technique like this? Well, sometimes we encounter integrals, that is, areas under curves, that represent the product of two functions, and these integrals simply can't be solved using the basic integration techniques, like simple substitution, that you've already learned. That's where integration by parts comes in. It provides a method to tackle these more complex integrals. In the following slides, we'll see exactly how it works, starting with the derivation of the formula itself. Derivation of the formula. Okay, so far we've established that integration by parts is essentially the reverse of the product rule from differentiation. Now, on this slide, we're going to derive the integration by parts formula, meaning we'll build it up step by step from the product rule. This will help you understand why the formula works, not just how to use it. Let's begin. To understand where the integration by parts formula comes from, we'll start with the product rule of differentiation, which you've already learned. Now, let's consider two functions. We'll call them u and v. Importantly, both of these functions depend on x. Think of them as any two functions of x that you can differentiate. The product rule tells us how to find the derivative of the product of these two functions. In mathematical notation, this is written as d over dx of u times v, and it's equal to u times dv over dx plus v times du over dx. So essentially, the derivative of the product u times v is the first function u multiplied by the derivative of the second function v plus the second function v multiplied by the derivative of the first function u. Keep this rule firmly in mind because we're going to use it as our starting point for the derivation. In the next steps, we'll integrate both sides of this equation to arrive at the integration by parts formula. Derivation of the formula continued. Now, in this step, we're going to integrate both sides of the equation we derived from the product rule. The equation we had was the derivative of u times v with respect to x equals u times the derivative of v with respect to x plus v times the derivative of u with respect to x. So, we're going to apply the integral symbol, which looks like a stretched out s, to both sides of that equation with respect to x. This gives us the integral of the derivative of u times v with respect to x equals the integral of u times the derivative of v with respect to x plus v times the derivative of u with respect to x with respect to x. Now, here's a crucial point that relies on something called the fundamental theorem of calculus. This theorem essentially states that integrating a derivative undoes the differentiation. In other words, the integral of a derivative of a function just gives you back the original function. Therefore, the integral of the derivative of u times v with respect to x simply becomes u times v. This simplifies our equation to u times v equals the integral of u times the derivative of v with respect to x plus the integral of v times the derivative of u with respect to x with respect to x. Okay, so let's move on to slide 3. As we discussed on the previous slides, we're building up the integration by parts formula from the product rule. Remember, integration by parts is essentially reversing the product rule. Keep this in mind, because on the next slide, we'll manipulate this equation further to isolate the integral we're interested in, ultimately leading us to the integration by parts formula. We're essentially rearranging this equation to solve for a specific integral, and this is a key step in the derivation. Derivation of the formula continued. Okay, let's move on to step 4. As we've seen in the previous slides, we started with the product rule of differentiation and integrated both sides. Now, we're at a point where we want to isolate a single integral. That's what rearranging the formula helps us achieve. Currently, we have an integral on both sides of the equation. To make it easier to work with, we're going to move the integral of v times the derivative of u with respect to x to the right-hand side. So, we're taking the integral of v du over dx. That's v multiplied by du by dx, integrated with respect to x, and moving it across the equals sign. Remember that moving a term across the equals sign changes its sign. This gives us the equation. The integral of u times the derivative of v with respect to x, which is written as u dv over dx, integrated with respect to x, is equal to u times v minus the integral of v times the derivative of u with respect to x, which is v du over dx, integrated with respect to x. This rearranged formula is crucial because it allows us to focus on integrating just one term at a time. In the next slide, we'll see how this leads us to the general integration by parts formula that you'll be using to solve problems. So, make sure you understand this step before we move forward. The general formula. Up until now, we've been using the variables u and v in our derivation. But it's more conventional to represent our functions as f of x, which we'll call our first function, and g of x, which we'll call our second function. Think of it as just a change in notation to make things a little clearer and more consistent with how you'll see this formula presented in textbooks and exams. Now, if we let u be equal to f of x, and the derivative of v with respect to x, that is, dv by dx, be equal to g of x, then we can easily express what we need to calculate. This means the derivative of our first function, f of x, is simply f prime of x, and the integral of our second function, g of x with respect to x, is just the integral of g of x. Keep these two results in mind, as they are crucial for applying the formula. Now let's substitute these definitions of u, v, du by dx, and dv by dx back into the integration by parts formula we derived earlier. This gives us the standard formula you'll be using from now on. The integral of f of x times g of x with respect to x is equal to f of x, multiplied by the integral of g of x with respect to x minus the integral of f prime of x, multiplied by the integral of g of x with respect to x with respect to x. Let's break that down one more time in plain English. The integral of a product of two functions is equal to the first function multiplied by the integral of the second function, minus the integral of the product of the derivative of the first function and the integral of the second function. Okay, so we've spent the last few slides carefully deriving the integration by parts formula, starting from the product rule. Now, let's put it into a form that's most commonly used in high school calculus. It looks a bit complicated written out, but it's a systematic process. Remember, we're essentially reversing the product rule. And in the next slide, we'll see this formula in action with a concrete example so you can really get a feel for how it works. Illustrative example. Okay, so now that we've derived the integration by parts formula, let's put it to work with an example. On this slide, we're going to evaluate the indefinite integral of x times e to the power of x, written as integral x e to the power of x dx. Now remember from the previous slides, the key to using this formula is correctly identifying our first function, f of x, and our second function, g of x. So, step 1, identify the functions. We need to split up this integrand, that's the part inside the integral sign, into two parts. A good strategy is often to choose the function that simplifies when you differentiate it as your f of x in this case. Let's choose x as our first function. So f of x equals x, and that makes e to the power of x our second function. So g of x equals e to the power of x. Now step 2, find the required components. The formula needs the derivative of our first function, f prime of x, and the integral of our second function. Let's calculate those. The derivative of x with respect to x is simply 1. So f prime of x equals 1. Next, the integral of e to the power of x with respect to x is, of course, e to the power of x. So the integral of g of x which is the integral of e to the power of x, equals e to the power of x. Great, we've now identified f of x, g of x, f prime of x, and the integral of g of x in the next slide. We'll substitute these values into the integration by parts formula and continue solving the integral. Illustrative example, continued. Okay, let's move on to slide 7. As we established in the previous slides, we're tackling the integral of x times e to the power of x, written as integral of xe to the power of x dx. We've already identified our functions. F of x is x, and g of x is e to the power of x. We also found that the derivative of f of x, which is f prime of x, is simply 1, and the integral of g of x, which is the integral of e to the power of x dx, is e to the power of x. Now, in this step, we're going to apply the integration by parts formula we derived earlier. Remember the formula? It's integral of f of x times g of x dx equals f of x times integral of g of x dx, minus integral of f prime of x times integral of g of x dx, all with respect to dx. Let's substitute our values. Instead of integral of f of x times g of x dx, we have integral of xe to the power of x dx. F of x is x, so we have x multiplied by the integral of g of x, which is e to the power of x. That gives us x times e to the power of x. Then, we subtract the integral of f prime of x, which is 1, multiplied by the integral of g of x, which again is e to the power of x, so we have minus integral of 1 times e to the power of x dx. Moving on to step 4, we need to solve the remaining integral. Notice that the integral of 1 times e to the power of x dx is simply the integral of e to the power of x dx. And we already know that the integral of e to the power of x dx is e to the power of x. Therefore, our integral becomes x times e to the power of x minus e to the power of x plus a constant of integration, which we denote as c. Don't forget that constant, as it's crucial for indefinite integrals. So, we've successfully used integration by parts to transform the original integral into a much simpler form. In the next step, we'll just do a little bit of simplification to present our final answer in a cleaner way. Illustrative example, continued. Now, looking at our current result, we have the integral of x times e to the power of x dx, which equals x times e to the power of x minus e to the power of x, plus c. Notice that both terms on the right-hand side share a common factor of e to the power of x. To make the answer look a little neater and more presentable, we can factor out e to the power of x. This means we rewrite the expression as e to the power of x, multiplied by the remaining terms inside the parentheses. So, we have the integral of x times e to the power of x dx equals e to the power of x, multiplied by the quantity x minus 1, plus c, and there you have it. This is our final, simplified answer. Remember that the c represents the constant of integration, which is crucial for indefinite integrals. Okay, let's move on to the final step of this example. As we've seen, we've used integration by parts to transform the original integral into a manageable form. Now, before we move on, let's quickly recap the key takeaways from this example and the entire integration by parts process. This will help solidify your understanding and prepare you for tackling more complex problems. Key takeaways. Okay, let's recap what we've learned about integration by parts. This slide summarizes the key takeaways, so pay close attention. First, let's remember where this whole technique comes from. The origin of integration by parts is deeply rooted in differential calculus. Specifically, it's essentially the reverse process of the product rule. Remember the product rule? It helped us find the derivative of two functions multiplied together. Integration by parts allows us to integrate such products, something we couldn't easily do with simple substitution techniques, as we discussed at the beginning. Now let's look at the formula itself. It's crucial you memorize this. The integral of f of x times g of x with respect to x, and I'm saying that as integral from f x times g x dx, is equal to f of x times the integral of g of x with respect to x. That's f x times integral g x dx minus the integral of f prime of x, that's the derivative of f of x, times the integral of g of x with respect to x, all with respect to dx. It looks a bit intimidating, but we built it up step by step from the product rule, so hopefully, it's starting to make sense. What's the goal of all this? We don't just apply this formula for the sake of it. The objective is to transform a complicated integral, one that's difficult or impossible to solve directly, into a simpler integral that we can solve. It's a problem-solving technique, a way to manipulate the integral into a manageable form. Finally, let's talk about the components you need to successfully apply this formula. You need two things: the derivative of the first function, which we denote as f prime of x, and the integral of the second function, which is the integral of g of x with respect to x. These are the pieces you'll be calculating before plugging them into the formula. Keep these points in mind as we move forward. On the next slide, we'll discuss some common mistakes students make when using integration by parts, so you can avoid them and become proficient with this powerful technique. Common mistakes. So the first point here is incorrect order. Remember when we broke down the integral into f of x and g of x? Well, students often get confused and switch which function they assign to f and which to g. Now, mathematically, the formula will still work if you swap them. The integration by parts formula is symmetrical in that sense. However, swapping them can often make the resulting integral more complicated to solve, not less. The whole point of integration by parts is to simplify the integral, so choosing wisely is key. Think about which function will become simpler when you take its derivative. That's usually a good candidate for f of x. Next, we have forgetting the second integral. This is a super common mistake. You correctly calculate the first part of the formula, f of the x times the integral of g of x, but then you stop there. Don't forget that there's a second integral you must calculate, the integral of f prime of x times the integral of g of x. It's easy to get focused on the first part and overlook this crucial step. Always double-check that you've accounted for both integrals. Finally, let's talk about sign errors. The integration by parts formula has a minus sign in front of the second integral. It's easy to miss this, or to get the sign wrong, especially if either the integral of g of x or the derivative of f of x involves negative values. Pay very close attention to the signs throughout your calculation. A simple sign error can completely throw off your answer. Okay, let's move on to the final slide, where we discuss some common pitfalls to avoid when using integration by parts. This is really important, because even if you understand the formula perfectly, these little mistakes can easily trip you up. So, to recap, choose your f and g functions strategically, remember to calculate both integrals, and be meticulous with your signs. Keep these points in mind, and you'll be well on your way to mastering integration by parts.